boundary as your variable goes from one limit to the other. So actually, this makes a nice exam problem.
Oh god.
Yeah.
Damn.
Thank goodness.
So what is XZ? Where is that?
Oh, I just picked an integrand.
I mean, so you just like, that doesn't do anything with this?
Yeah, that has nothing to do with the setup. I could have put God knows what in here. Yeah.
Oh,
Well,
there's
maybe
no
it was this
relation
problem.
to that.
Okay.
That's,
The only way in which the integrand influences the setup is if there's more than one way to come up with limits, and usually there's going to be more than one way. I could have chosen functions like x being a function of y and z for my bounds, and then used this triangle or this triangle. I could have done tetrahedron in many different ways, but different choices lead to something different to anti-differentiate, and sometimes you can get something that's a real pain. So even though your setup is right, you get something that might be impossible to integrate, and you have to go back to the drawing board and try a different way. There was an example involving double integrals where this came up, where the integrand was e to the y cubed. So by changing the order of integration is something that we're able to do.
so that xz doesn't have a correlation to the coordinates.
No. So it's just
It could
yeah.
be arbitrary different variables there.
Yes.
So what exactly are we integrating? Like, I mean, I just don't see what exactly a triple integral is, I guess.
Oh,
I mean, like, I get that the double integral is like the area of that, I mean, the volume of that.
oh, to get volume. Yeah. So you're saying what is the geometric meaning?
Yeah.
So there is no direct link, like how you have single integrals being area, double integrals being volume. So you don't have that same kind of generalization for triple integrals, and that's actually why I was talking about the stuff involving mass or moments of inertia, because that is a use. Where if you have any quantity that's defined for every point in a three-dimensional object, and you need to say take an average of that quantity, for instance, that's where the triple integral is going to come into play. So it's useful for things like anytime you have a formula such as density times volume or formulas of that type, that's where it's defined over a three-dimensional object. That's where triple integral is useful.
So in this case, like, XE could be, the density.
It's playing the role of a density, yes. Yeah. Now, that's just or equivalently, maybe this could be some kind of, maybe I'm computing a moment here, and if I'm computing a moment of an object around the YZ plane, then I had to put X here, and Z is my density. Yeah, so it could be something like that. So yeah, it's unfortunate that there is no obvious geometric application like there was before, but there still are plenty of uses. One of the things that we'll talk about at the end of the semester, since we've seen plenty of partial derivatives, there's partial differential equations, and a lot of times the solutions to those are expressed in terms of triple integrals as well. All right. Okay, so, any other questions about the setup? All right, how are we doing on time? Okay. So, now we've gotten to this point, fortunately, the actual evaluation is not going to be so difficult. First, I'm integrating with respect to z, but here I have an x. This x doesn't need to be here, it's just a constant factor, so I can pull it out. In fact, I can put it here, because my second integral is with respect to y, so I can pull the x outside of that as well. Because you're just treating it as a constant. So now I'm just going to integrate z from 0 to 1 minus x minus y. And what it's going to give me is z squared over 2, evaluated at 0 and 1 minus x minus y. dy dx. So now we're just going to have, we'll plug in our limits. All we're going to get is, okay, we have an x here. And we're going to get a 1/2. I'll just pull out the 1/2 too. We're just going to get 1 minus x minus y squared dy dx. Okay. Now, so now we need to integrate this with respect to y. Now what we could do is multiply all this out. But we don't actually need to do that because, as a convenience, if I have like a constant c minus x raised to a power, and I want to integrate that with respect to x, just in general, how would this go? What would the, so without bothering to multiply it out,
Just like normal, you'd integrate the entire inside as if it were just an x or whatever, right? You still increase the power by 1, you still multiply by, or I'm sorry, divide by n plus 1.
right, as long as you're careful about the minus. So we actually get a minus c minus x to the n plus 1 over n plus 1. Because then what's going to happen when you differentiate this, okay, you'll bring down the n plus 1, cancel with that. This is now raised to the n. But if you differentiate the inside and you get a minus, that will then cancel with this minus. So as long as you include the minus, because it's the x that's being subtracted, then you're okay. All right, so you don't have to bother multiplying this out. So what's going to happen here, when we anti-differentiate this, what's it going to turn out to be?
Negative 1 minus x minus y cubed over 3.
X minus y cubed over 3, evaluated at 0 and 1 minus x dx. All right, we have this 1/3 here. Let's just pull it out. Okay. So now we plug in the limits. Y is going to be equal to 1 minus x and 0. But when we plug in y equal 1 minus x, everything here is going to go away. It's going to cancel with this 1 minus x. When we plug in 0, we're just going to get 1 minus x. And because of the lower limit, that's being subtracted, this minus will be turned positive. So we get 1/6, integral from 0 to 1, x, 1 minus x cubed dx. Okay. So, realize I did a lot in that step. Okay. So in case any of that was missed, we get minus 1 minus x minus 1 minus x cubed minus 1 minus x minus 0 cubed. That's what happened when we actually plugged in the limits. So that's why all that went away. This became a plus, and we get 1 minus x cubed over here. So now we're left with this. What's the easiest way to do this? There's two ways that that you can think of pretty quickly. One's kind of tedious, the other's not nearly so. Imagine if it was something much higher than 3. Imagine it's x times 1 minus x to the 10. That would definitely lead to a preference. By parts? No, we don't need to do by parts. Okay. What?
U substitution.
Yes, what U substitution?
Oh,
Or you're just throwing it out there just for...
If I was doing it, I would have just, since it's just cubed, I'd
Yeah.
have just expanded it.
You would... Okay, but...
We're not doing that.
Yeah.
I know. So that,
Actually, I was talking to Dr. Kolobal yesterday. That's what he likes to do. He likes to put out problems that, if you can see what the right way, that the simplest way is, it's actually pretty easy. But otherwise, you're just going to spend all your time.
that would be something that he would do.
Yes. So u is 1 minus x. So then du is minus dx. All right.